Okay, so good morning, good afternoon, or good evening. It's really a pleasure to present this topic to you. I will start my presentation with some introduction, some introductory information, and then I will discuss which uncertainty components typically affect our measurements. And then I will discuss how to quantify combined and expand the combined standard uncertainty to allow us to have a result with a high confidence level. And I will discuss how to use in-house validation data to perform this evaluation. Then I will try to list some frequent mistakes that I found in labs as technical assessor of accredited labs. To highlight the need to pay attention to some details when you use this type of approach. And then I will close with some final remarks. But before we move on to the uncertainty evaluation details, let me describe the measurement process. Typically, labs perform analysis because they need to do that. There is a need for analysis. There is a problem that somehow can be solved or from where chemical analysis can be useful to solve that problem. And then typically it is defined some measurement requirements. Typically we define requirements for the method that is being used. I'm using the term method. If you follow the international vocabulary of metrology, probably you would use procedure. Okay, but so they define requirements for the method regarding the analyte levels or the concentration levels of the analyte. And now the word concentration I'm using in a general sense, can be mass fraction, can be conductivity, can be pH. So you have to define analytical scope regarding the analyte concentration, type of matrices, and then typically you have to define a maximum admissible uncertainty, a target uncertainty as a relevant requirement for your measurements. And typically you can add additional requirements like the cost of analysis. And then you develop a method, or you take a method from a reference and implement it, get the chemicals, the instruments, and the expertise to perform the analysis using the method. And then you have to perform the method validation. And at this stage, typically you collect performance data. And this validation culminates with the comparing the estimated or the evaluated measurement uncertainty with the target or maximum admissible uncertainty. And then after this stage, you are allowed to analyze your unknown samples, and you do that with the support of test quality control, because a valid method can produce not valid results, and you have to check the performance as you do the analysis of unknown samples. And then you take decision on tested samples, typically taking the measurement uncertainty into account. Okay, like Ivo already mentioned, measurements are affected by different effects. Random effects that occur within a day are some of those effects. So if you do if you repeat an analysis in the same day by the same equipment using the same from the same analyst, typically you will not get the same number as you do replicate analysis. And this is due to within the random effects that can be quantified by the repeatability standard deviation. So notation for this standard deviation that we will use is the S and the subscript lowercase r. But measurements are also affected by the so-called between days random effects, because we know that typically if you do the analysis in different days, the dispersion of results is larger than if you do in the same day. And this is due to the impact of the day, somehow daily conditions on the measurement results. And this can be quantified by the between days standard deviation with notation S underscore subscript B. But measurements are also affected by systematic effects that systematic effects that remain even if you do the analysis in different days. And that systematic effects are also responsible for the measurement error, for the difference between the measured value and the reference or conventional true value of the measurement. And the discrete precision standard deviation that we quantify, if we use different notation, use SRW for this standard deviation. Some people use the within laboratory reproducibility standard deviation instead of iterate precision standard deviation. Okay, and this standard deviation is in fact a combination of the repeatability and the between days variance. And this term is very important for uncertainty evaluation. And we must be aware that systematic effects will be assessed by the lab, but our assessment will always be affected by some systematic effects. So our understanding of systematic effects, will always be affected by random effects. But we can try to minimize the impact of random effects when we assess systematic effects. For the evaluation of measurement uncertainty based on in-house method validation, typically we take into account three components: precision component, recovery or bias component, and then you have, in some cases, to quantify additional or other uncertainty components not expressed in the first two components. And I will discuss how to manage the uncertainty component, recovery component. I will describe briefly how to do that because I will have a second presentation on this, and then I will also discuss examples of other components. And the idea is to quantify the uncertainty of the measured value. Notation here is lowercase q for quantity, because it can be any type of quantity: concentration, mass fraction, as you wish. So first, the precision component. First of all, let's start by the case where our sample is analyzed only one time. So we have a single measurement of our sample, and the standard uncertainty for measurement precision will be exactly the standard deviation of measurement intermediate precision. So we just need to have this number, intermediate precision, to know the uncertainty from precision. But occasionally, the unknown sample is analyzed n times in n different days. This is not so frequent, but in some fields, if the product is not compliant, you analyze a second time by a second analyst, and you report the mean of results from 2 days. In this case, if the duplicates in 2 days agree with each other, you report the mean of 2 results, and the standard deviation or the standard uncertainty for measurement precision so the intermediate precision of these duplicates obtained in 2 different days will be the intermediate precision standard deviation divided by square root of 2. In this case, 2 days. So your precision gets better when you decide to do the analysis several times in n days. It will be square root of n times better. But most labs, they do replicate analysis in the same day under repeatability conditions. So, and if they report the mean of m results performed in the same day, the standard uncertainty of measurement precision will be lower than if a single measurement is performed, but will be not as low as if we do in different days. And the formula that should be used is this one, that depends on your on the known precision standard deviation and the repeatability standard deviation. This formula is very useful to allow you to know how better your measurement is if you do replicates under repeatability conditions. But When we assess the uncertainty from measurement precision, one of the most difficult things is to handle how precision varies with the concentration. And this is important, of course, if our analytical method is applicable to a wide concentration range. And for this reason, in that cases, we should try to define models of the precision variation with the concentration. To do that, we can rely in very well-known trends of precision centered in the known limit of quantification. We know that typically below 2 times the limit of quantification, and this is more adequate if the limit of quantification is estimated under the precision conditions. Okay, we know that typically below 2 times the limit of quantification. A notation here for limit of quantification is this one: Q for quantity, LOQ for limit of quantification. Okay, so typically below this 2 times this limit, the precision standard deviation is approximately constant in an absolute way. And we know that above 2 times the limit of quantification, typically the precision is constant in a relative way, as a relative precision standard deviation. That is, in fact, the precision standard deviation divided by the concentration itself. So after this 2 times limit of quantification, the precision gets constant in a relative way. Some people prefer to use 5 instead of 2, but this is not really a big issue. The model of precision variation with concentration can be further improved if you add additional intervals, or if you divide your analytical interval in more intervals above 2 times the limit of quantification. So how it works? So typically you define a first interval that is between the limit of quantification and 2 times limit of quantification, where the precision standard deviation is constant. You have an interval 2 typically between 2 times limit of quantification and 10 times that limit, where we have a constant relative precision standard deviation, and typically you have another interval between 10 and the maximum concentration of your analytical range, where we have a constant relative precision standard deviation that is a little lower than interval 1. Okay, interval 2. Interval 1 is rather narrow, I would say, but this is a very important interval in many fields. In many fields, most decisions are taken close to the limit of quantification, and this interval is rather different from the other intervals or of our analytical scope, and this is why we have to pay attention to this specific interval. Let me give you an example how this could work by giving you an example of the simplest way of dealing with the precision variation with the concentration. It cannot be more simple than this. So if you decide to quantify the precision standard deviation at 2 times the limit of quantification, and you get this the standard deviation at 2 times limit of quantification, this is notation there, you can use it to estimate the precision at interval 1, because it is exactly that standard deviation. So how it works graphically? So you assess the precision standard deviation at 2 LOQ, and then you somehow extrapolate that information below this limit until the quantification limit. For interval 2, what should we do? We should look to the precision as a relative intermediate precision standard deviation, and then we take that relative standard deviation above 2 times limit of quantification. This apostrophe is for a relative quantity, in this case a relative standard deviation. If you want to be more detailed, because you have more time to do your validation, Sometimes you don't have time. You have to do a fast validation to fix a problem from your flexible accreditation scope, and you can do as I described. But if you have more time, you can collect more data about your measurement precision. Typically, you perform several analyses in different samples in different intervals, and you pull all that standard deviations available. So let me give you an example. In interval 1, in this narrow, very important interval between limit of quantification and 2 times limit of quantification, you pull available standard deviations. Use this pooling where the degrees of freedom of this standard deviation is taken into account. In this example, so we calculated the intermediate precision standard deviation at 3 concentration levels in this interval 1, and then you pull them, and we got a single standard deviation that describes all this interval 1. For interval 2, you have to pull all that information, but as relative intermediate precision standard deviation, so we have different of those, and in this case 3 of those that were pulled, and then you after pulling you get a single relative intermediate precision standard deviation that will be applicable above 2 times the limit of quantification. You can improve your model if you get an additional interval above 10 times the limit of quantification. Basil Magnussen will say some more things, additional things on this subject. Now, we just described how to evaluate the precision and uncertainty, and now let's go to the recovery uncertainty. I will present a simple example, and I will present some more details in a second presentation. But first of all, I would like to say that to evaluate the recovery uncertainty, we have to take into account that we need to analyze at this stage samples with unknown concentration. So to assess precision, we don't need to know the reference value of the samples, but to assess recovery, to manage the systematic effects, you need to analyze samples with known concentration. And typically, at this stage, you have also to take to assess if the observed systematic effects are relevant or need to be corrected on results. Typically, you should correct the results for recovery, or if it is mandatory, you must. If you are allowed, I would say you should do it because typically it will improve your estimate. But in some fields, you are not allowed to correct the results for recovery, and you have to assess how this impacts in your uncertainty. Steve Ellison tomorrow we'll also discuss how to handle allowed limits for recovery. That is also relevant, the management of this recovery uncertainty. Okay, but let's give an example how this can be done. And the example that I'm presenting to you is the case where the mean recovery or your systematic effect is assessed from n participations in proficiency tests, okay? And in cases where the sample from proficiency test is only analyzed one time, once, okay? If it is analyzed more times, you can adjust the formulas, but it will be a little more complex than this one. Okay, in this case, the mean recovery will be the mean of all recoveries, where each recovery is calculated by this term, is the ratio between the measured value and the reference value. So lowercase q for the measured quantity, uppercase q for the reference value of that quantity. Okay, if you do that, the standard uncertainty associated with the mean recovery, associated with this mean estimated recovery, this standard uncertainty will be the square root of the sum of these terms, where for each participation in the proficiency test, we have a term here for the recovery. So this is the recovery for each participation in the proficiency test, the square of the recovery. And here we have the relative standard deviation of measurement intermediate precision. Okay. Since we only perform one analysis of this sample, this comes from models, precision models, the ones that I just described to you. And then here we have the relative standard uncertainty associated with the reference value. And yes, all this is inside the square root, and n is outside. The formula is correct. Many people ask why the n is outside. Everything is correct. You just need to follow and to apply the uncertainty propagation law to this mean recovery formula, and you will see that n will be outside. I will present more examples, more scenarios, and even examples of the management of this mean recovery uncertainty. Okay, but at this stage, we are not finished. Why? Because we know the recovery and the standard uncertainty of the recovery, but the recovery can be 99% or can be 30%. Okay, and the uncertainty of the recovery is only how good you know that the recovery value that can be very different from 100%. So at this stage, we have to assess if the mean recovery is equivalent to the ideal target value, typically 100%. And this can be done by performing a t-test, somehow a t-test, where instead of a standard deviation, we have a standard uncertainty. So it is an updated t-test, I would say, where we compare this term with a value of 2, typically value of 2, that is the absolute difference between 100% recovery and the mean recovery, divided by the standard uncertainty of the recovery. If this term is smaller than 2, so you have your mean recovery is equivalent. I like to say meteorologically equivalent to 100%, and therefore we don't need to correct the result, the original result for recovery. If this condition fails, you should correct the result for recovery by dividing the original measurement by the mean recovery, and you get your correct result. So we just described how to quantify the uncertainty for precision recovery. Additional uncertainty components can be relevant. Sometimes we have uncertainty components that are not expressed by precision and trueness and recovery component. One example is the heterogeneity of the samples. Sometimes the samples analyzed for precision studies and for recovery studies are more homogeneous than real samples, and in that case you have to add an additional component for sample heterogeneity. For interval 1, so where absolute precision is constant, you can calculate this term as the square root of the square of the difference between these two terms. So the first term, this is the absolute, this is the mean of ranges of duplicate results from the analysis of heterogeneous samples. So we have different heterogeneous samples. You do duplicate analysis. You have the absolute value of the difference, different ranges for different duplicates. You take the mean, divide by 1.128, and this is the repeatability standard deviation for the analysis of heterogeneous samples. If you do duplicates for the analysis of homogeneous samples, you have and if you have the mean range of duplicates of homogeneous samples, divide by 1.128, and you get the repeated standard deviation of these homogeneous samples. If you subtract both, you will get only the component due to heterogeneity as an additional uncertainty component. You can also take as additional uncertainty component the sampling uncertainty. So sometimes the sampling uncertainty needs to be considered in our uncertainty evaluation, because our aim is to assess an item larger than the laboratory sample, and in that case we have to take into account sampling uncertainty. You have in this slide two listed examples, or how to handle this uncertainty depending on the purpose of your analysis. And now, how to combine everything together, and in this case assuming that there is no relevant additional uncertainty component. How can we do that? So for interval 1 between limit of quantification and 2 times limit of quantification, our expanded uncertainty for approximately 95% confidence level will be 2 times, this is coverage factor usually used for this confidence level, 2 times the square root of the sum of the square of the standard uncertainty from measurement precision, plus a component absolute for the systematic effects for the mean recovery. That will be the relative standard uncertainty of the mean recovery times the measured value. And the measured value can be the original value or the corrected value, depending on your scenario. For interval 2, above 2 times limit of quantification, typically components are combined relative, because performance is rather constant in a relative way. You have here the relative precision standard deviation, the square of this standard uncertainty, the square of the relative standard uncertainty of recovery, the measured value, original or corrected, and the expansion factor again. Let me close with frequent mistakes. I would say that accredited labs produce. Frequently, labs manage the variation of precision with concentration not very well. They assess precision, or the relative standard deviation of precision, above 2 times limit of quantification, and then they try to apply it below 2 times limit of quantification, and this of course will underestimate precision in these in lower concentration levels. Another problem that frequently occurs is that to quantify limited precision standard deviation, labs take results from the analysis of the same sample, but this sample is analyzed in different days, okay, but occasionally the same day, we have replicates in the same day. So this standard deviation will be a mixture of repeatability and limited precision, and this is not correct. Another very frequent problem nowadays is that labs calculate an uncertainty that is not compatible with the quality control criteria. Imagine the uncertainty is, expanded uncertainty is 10%, and then the quality controller of a control standard accepts difference of 20%. And they must be careful with matching that. So let me now close saying that we must be aware that the reported uncertainty is much more than performance, and the uncertainty of the reference values is more than that. Expresses the way information is processed, is managed, how the same performance data is treated and managed. So in fact, in uncertainty, I would say that you do not get what you see, you get how you see, how you look to the same data impacts on the reported uncertainty. And then to close, let me tell you that top-down uncertainty evaluations are very popular. for their simplicity, but sometimes the simplicity of these evaluations hide relevant details, and labs perform inadequate evaluations. And I would like also to pass the following message. So at this moment, we are about 22 years. We celebrated 22 anniversary of the first edition of the 70,025 standard that introduced the measurement uncertainty concept in accreditation. And it is important to mention the accreditation because accreditation is what it is internationally accepted as an evidence of competence of labs. So we celebrate the 22 years of the introduction of the uncertainty concept in accredited labs. But nowadays, uncertainty evaluation is more important because we are using it for conformity assessments. So this is time to pay attention and to look more carefully for our uncertainty evaluation. So thank you very much for your attention, and sorry for taking 30 minutes for that.